Hi guys, welcome back to the world of mathematics. In the previous lesson, we learned about the fundamental theorem of arithmetic. In today's class, we'll be learning about irrational numbers and their proofs. The symbol used by mathematicians to represent the ratio of a circle's circumference to its diameter is nothing but pi. So let's write that down. You have your circumference by your diameter, which is equal to pi. Now, what's the value of pi? Pi is approximately equal to 3.141592653 and so on. So let's just remember the first few decimals. So it's 3.141. The expansion goes on and never terminates. The expansion never repeats as well. These are the features of irrational numbers. First, let's understand what rational and irrational numbers are. An irrational number cannot be written in the form of p by q. So, an irrational number cannot be written in the form of p by q. It cannot be written in this form. And a rational number, however, can be expressed as the ratio of two integers with the denominator not being equal to 0. So what did we just say here? An irrational number cannot be written in p by q form, but a rational number can be expressed as the ratio of two integers where the denominator is not equal to 0. Nothing but rational numbers can be written as p by q form, can be written in the p by q form where q is not equal to 0. So in this lesson, we will discuss about the theorem based on FTA, which is nothing but fundamental theorem of arithmetic, and also we'll talk about a very important topic, which is proof by contradiction. There is a prerequisite that is required to prove that an irrational number is irrational. So here's what the theorem states. Let p be a prime number, and if p divides a square, where a is a positive integer, then p divides a. So what's it saying? It's saying let p be a prime number, right? And if p is a prime number and p divides a square, then p also divides a, given that a is a positive integer. Now let's look at the steps where we can prove this theorem. There is a prerequisite that is required to prove that an irrational number is actually irrational. Now the theorem states, let p be a prime number, and if p divides a square, then p must also divide a, where a is a positive integer. Now we said that p divides a square, right? So if p has to divide a square, then a must have a factor p. Isn't that right? If p has to divide a, then it must have a factor p. From the FTA, we can say that a is equal to x into p, where x and p are prime factors. That's right. So here x and p are prime factors.